Everybody, this is Chérif Matta from Canada. I thank you for coming to my talk. I would have liked to deliver this talk in person, but unfortunately, due to a technicality, my Indian visa has been denied at the last minute. At the beginning, I'd like to thank the organizer of the IUCr 2017, Professor Desiraju and his team. And also I'd like to thank very much Professor Anna Kravsuk for inviting me to her symposium. And also I'd like to thank Mr. Tiwari, the AV manager, for facilitating all the glitches of the audiovisual streaming. And thank you very much for coming to my talk again, and I hope you enjoy it. Thank you. Today I would like to introduce what I have termed the localization-delocalization matrices, or LDMs, which is an approach by which a molecular descriptor is constructed that uses chemical graph theory tools to manipulate and extract information from matrix representations of molecules using the results of QTAIM calculations, the quantum theory of atoms in molecules of Bader. These results are used as raw material or raw input into these matrix representations. In the literature, there are thousands of molecular descriptors. These descriptors are usually designed to predict empirically certain properties, certain molecular properties. Some of these descriptors deliver, for example, physicochemical properties. Some of them are better for kinetics. Some predict biological, pharmacological activity. Some work better for thermodynamics, etc. But it is unusual to find descriptors that work properly for more than one of these classes of properties. I hope to show you that today that LDM may be able to do so. So the outline of my talk is in front of you here. I will talk about molecules as networks, and then I will describe the LDMs and their applications, and a few notes about an extension to the Bader-Gatti source function. So first, molecules as networks. Networks come in two varieties. A network can be a complete network or can be an incomplete network. A complete network is a network whereby every vertex is connected to every other vertex by an edge. So number 1 here is connected to 6, 2, 3, 4, 5. An incomplete network is one in which not every pair of vertices are connected by an edge, such as this one. Most chemical formulae, most chemical graphs are in fact incomplete networks, except diatomics, which by necessity are complete. We represent chemical structures such as these in different ways. An abstract representation of a molecular structure, one of the simplest possible way to represent the chemical structure is this one, in terms of a matrix. You label the atoms, here only the carbon atoms in this case, and every time you have a bond between any two atoms, you have a 1, and when there is no bond, there is a 0. Of course, this labeling is non-unique, since it is arbitrary, and therefore the matrix representation is non-unique, and hence it requires mathematical tools to extract matrix invariants from these matrices. In other words, properties of the matrix that do not depend on the numbering or the ordering of the columns and the rows of the matrix. That's the point. This is where we use chemical graph theory tools in order to manipulate matrices constructed not from 1 and 0, but rather from QTAIM based properties. So here is the first example. This is the molecular graph based on the bond path in two molecules of water, a dimer, a water dimer, hydrogen bonded here. And we can improve on the simple connectivity matrix that I showed you by 1 and 0 by weighing the ones with a property that depends on the bonding between any two atoms. So for example, here, the weight is the bond critical point electron density. So oxygen 1 and H3, oxygen 1 and H3 here, the density at the bond critical point is 0.371. So that's the number we input here, and so forth. This is a simple form of a representation of the molecular graph, and it is not without problems because many of the molecular properties are continuous and do not depend on the making and breaking of bond in a discontinuous way. And a better matrix would be a matrix that is full of numbers, even if some tend to zero but not exactly zero, such as a matrix based not on the bond the bond path weighted connectivity matrices like this one, but rather using something like the electron delocalization indices also obtained from QTAIM. So in other words, I would like to contrast two types of molecular graphs. The normal familiar molecular graph, such as this one, whereby it is an incomplete graph, this one, whereby every atom is connected with every other atom in the molecule by a line of electron delocalization. So that leads me to discuss the localization-delocalization matrices, or LDMs, and some of their recent applications. The idea has been described for the first time in this article that appeared in 2014 here, and the term was introduced in this article as well. So the quantum theory of atoms in molecules defines a localization index and a delocalization index. As Richard Bader used to say, the electron goes wherever its exclusion hole goes. If the Fermi hole is localized, so is the electron. If we integrate the exchange or exchange correlation density of an electron of a given spin, say the alpha electrons over one and the same volume, say a QTAIM atomic basin, for example, and if we do the integration twice over the same basin, A here, for instance, once varying the position of the reference electron and once varying the position of the hole, we get minus the number of alpha electrons in this volume. If we do the same for the beta electrons, and we sum the magnitudes, since the Fermi correlations of the same spin electron is negative, so we take the absolute value here, like these. We do it for the alpha and the beta. We count the total number of electrons confined within this basin, in other words, not exchanging with the external world. In contrast, we can define also a delocalization index between a basin, say this yellow basin and the green basin here, if we allow one integral to run over one atomic basin while the other run over the other basin. In this case, and we do the same and we have to multiply by 2 here, we count the number of electrons shared between these two atoms, in this case that nitrogen atom here and this oxygen. So we can now define the localization-delocalization matrix, or LDM. The LDM is a symmetric matrix whereby along the diagonal we list the localization indices of the individual atoms. So this is the localization index of atom 1, of atom 2, of atom n, and the off-diagonal elements consist of half of the delocalization index between that atom and every other atom in the molecule. So this is the delocalization index between atom 1 and 2, atom 1 and 3, atom 1 and n, etc. Of course, it is a symmetric matrix, and therefore the sum of the rows or columns, whether you sum this way or you sum this way, give you the population, the atomic population of the atom, and of course the sum of the population at the end give me n, the number of electrons in the molecules. It's an n by n matrix where n is the number of atoms, and the property of this matrix comes from Bader's summation rule here, whereby the population of an atomic basin is given by a number of localized electrons plus half of the number of the delocalized electrons between that atom and every other atom, whereby J here is not equal to I. This number can be obtained as well by direct integration of the electron density over the atomic basin. So what then is the chemical information encoded within the LDM? A lot. The LDM, by its construction, give you electronic population, atomic charges, of course, because they are related to the populations, the atomic molecular volumes, because connectivity, the complete and fuzzy molecular graph, because it's continuous, it's not an all or none graph. It encodes for molecular geometry, the bond strength. You will see the whole talk today is about molecular similarity. You will see how this is used to define molecular similarity in a new way, and by definition and by construction, it codes for the entire pattern of delocalization of electrons in the molecule and the localization of the electron in the molecule. And the one example here is the well-known example of the population, the atomic population. So the sum of the column or row will give me the atomic population. If you add up the atomic charge in atomic units, so in this case 6 for carbon, you get the atomic charge for this carbon number 1 is 0.02, which this one you can get it by integration directly, but here is an example of a property that is coded here without being explicitly shown. So some applications of LDMs in quantitative structure to activity relationships. Okay, well, I have constructed these matrices. Now what? What do I do with it? How do I extract the chemical information contained in the LDM? How do I compare two molecules by comparing their matrices? The simplest possible thing comes from the Frobenius distance, which is essentially a Euclidean distance between two matrices. You take the corresponding elements of the two matrices and subtract them, square their magnitude, square them, and sum, and then take the square root of the sum over all the matrix elements. So here I first started to plot the Frobenius distance between acetic acid and its fluorinated derivatives. If you plot here the zero means I took that one as reference, so its distance from itself is 0. And as you go here, you can see that the dissimilarity of the acid with the reference is very strongly correlated with its pKa. I've tried to correlate all sorts of thermodynamic quantities of hydrocarbons, and it worked very well. We have about 60 or 70 similar plots as the one I'm going to show you, but I will show you only one. And in this case, a property that is relatively difficult to predict, which is the difference in boiling point between the different hexane isomers. It's a property that depends on branching, and it is very well predicted by the LDMs. So here we have the Frobenius distance of the LDMs from the reference being taken as the most branched isomer of hexane, which is 2,2-dimethylbutane, this one. And you can see again that the boiling point in this case is very well correlated with the distance from the most branched one until you reach the least branched isomer, which is N-hexane, the linear isomer. We went to a more difficult case of pKa, the pKa of parasubstituted benzoic acids. So the benzoic acids are different than the acetic acid because the perturbing group, the group that affects the pKa here, is distant from the active group upon which the property depends, the property being the pKa in this case. And they are connected by a linker, and the linker is this benzene ring in the middle here. And S here is for substituent. It's not sulfur, this is just substituent. So I change the groups here and look at the pKa's and see how we can correlate that. The work that I will show you is quite interesting because first we have taken the submatrices, we've taken the matrix of this part only of the molecule, sometimes even only taking the O2H1, the acidic hydroxyl here, this one, only the submatrix, so it's a 2x2 matrix here, or 4x4 in this case, the full COOH group. And if you take the hydroxyl, the acidic OH here, the R square is 9.7. If you take the whole group, the whole acidic carboxyl group here, the correlation R square is 0.99. You can see that. And also, it's worth noting that if you include any atoms of the linker in the correlation coefficient drops significantly. And that points to a possibility in the future to automate the detection of the active group responsible for the properties. In this case, we know it's pKa, but suppose that was a drug, and we don't know which part of the molecule is the active group. We could perceive in the future an algorithm that take random combination of atoms, and the one that shows the strongest correlation points at a possible active center. But this has work to be done in the future. Now, during that work, we had what I call a disaster first, but it turned out to be a triumph for the method. Because here is what happened. We had one of our candidates here, 4-dimethylaminobenzoic acid, is listed in the Handbook of Chemistry and Physics as having a pKa of 6.03. However, our LDM model predicted a pKa of 5.03. So that's a 1 pKa unit. This is huge. So that's a disaster. When we looked at the same handbook for a very closely related molecule, instead of dimethylamino, only 1 methylamino. So this is the 4-methylaminobenzoic acid, which is this molecule versus this one. We find that the pKa of that one is 5.04. You cannot expect that removal of that methyl from here would change the pKa by 1 pKa unit in this distant group. So that pointed to a possible error in the handbook. So we went to the primary literature, and sure enough, what we find in the primary literature is that 4-dimethylaminobenzoic acid has indeed 5.00 pKa, exactly as predicted by our model. So this should be corrected in the handbook. This value for 4-dimethylaminobenzoic acid, the pKa is 5.03, just exactly as we calculated, not 6.03. It's a typo in the Handbook of Chemistry and Physics. While it's not the end of the world to detect a typo, but it points to the strength of this method. If it contradicts what you have, look again. You know, it's a very predictive, very powerful method. Next, we looked at some other properties such as aromaticity of rings in molecules. So here, the studied system, this is what we studied, some benzene, naphthalene, anthracene, you know, up to 4 rings in different arrangement. So in this case, what we've done, you take the ring, we take the carbon skeleton only of the ring, and we form the matrix, the corresponding matrix. So this A matrix here corresponds to the A ring here. So these are the carbon number 1, 2, 3, 4, 12, 11. And then we calculate the Frobenius distance between these and the carbon skeleton of benzene. And we compare with known aromaticity indices. For example, in this case, the harmonic oscillator model of aromaticity of Krygowski and co-workers, the famous HOMA, the structural aromaticity index, and you can see that there is a very strong correlation between the Frobenius distance from benzene to the HOMA index. So indeed, the LDMs do capture at least the structural aromaticity index, but there are more indices in the paper that are also very well reproduced by our Frobenius distance of LDMs. There is a new method or a new idea that was advanced by Ron Cook, my collaborator in industry. He has proposed to use principal component analysis, PCA, to extract the patterns of information in the LDMs, treating them just like a table of data. So I will show you just one example. Corrosion cracking is the acceleration of the cracking due to corrosion of metals under stress. So you put a metal between two, you pull a wire here of a known cross-section by a certain given load, and the wire is subjected to environmental condition in this container here with adjustable temperature, with controlled temperature, ionic strength, pH, etc., with or without inhibitor of corrosion. And these inhibitors usually work by coating the metal and preventing the access of oxygen and or water to the surface. You can see in the curve the elongation versus load in kilograms per cross-section, per unit cross-section here. You can see that the air test, of course, the dry air test is what you should try to aim to, and the blank experiment is the worst. Of course, without any stress corrosion cracking inhibitor, and then you have several inhibitors. Note that the best three inhibitors, the one that get us as close as possible to the dry air test, are all sulfurated molecules. We have mercaptobenzothiazole, mercaptobenzoimidazole, and phenylthiourea. They all contain sulfur. So Ron Cook had plot first some of the eigenvalues that come out from the principal component analysis versus to predict the extension of the wire under a given stress. And there was a real problem here, is that there are three outliers. Every compound fall on the line very, very nicely here, except these three outliers that they fall totally out of the line. So he reasoned the following way. He said, well, maybe in the anodic current will oxidize these thiol group and dimerize these molecules, and then the active species are no longer the monomers, but rather the dimers. And this is what he proposes. He said, well, the phenylthiourea, the two mercaptobenzothiazole, can dimerize under anodic current into these dimers, for lack of a better word, forming these disulfide bonds. And he repeated the calculation. He did LDMs of these new dimer molecules. And when he did that and included with the other molecules, every candidate is now on the same line, including these most active one, the phenylthiourea, the mercaptobenzothiazole, and the mercaptobenzoimidazole. So and not only R square is 9,9, but the Q square, the leave one out cross-validated statistic, is also a very elevated, indicating that there is no overfitting and that this is a predictive model. So I haven't showed you most of the results, but we have data that shows that LDM can predict boiling points, enthalpy of vaporization, heats of combustion, enthalpies of formation, rate constants of hydrolysis, pKa's, corrosion inhibition activity, and even detecting the active species, ribotoxic activity of some antibiotics that could be used in as anti-cancers, mosquito repellent activity, including detecting the receptor in the antenna of the mosquito. There is a very beautiful paper that just appeared by Ron about that. And also you can use the LDMs to test the quality of the basis sets, giving it a dimension more than just the energy. It's not only the basis set that gives you the best energy, but also the one that is closest to the best basis set, essentially. So there are many, many other applications that I haven't showed you, and these applications are going to be described in this book that we are trying to finalize. Is Todd Keith, the principal programmer of Impact 10 and Codessa 3, and also GaussView. And Todd has sent me this message last year, which I use with his permission, he has tried to reproduce my pKa result, or our pKa results, on the parabenzoic, substituted parabenzoic acids. And he has tried his CODESA program that extracts thousands of descriptors ad hoc from the sum file and from the log file. And he has found that our LDMs match the best ad hoc predictor. This is very impressive because usually when you try ad hoc descriptor, chances are you're going to find something that is totally meaningless but with a very high correlation. So at the end, I'd like to extend this to the Bader-Gatti source function. Bader and Gatti showed that the electron density at any point in space can be viewed as consisting of contributions from all sources, local sources, at all other points in space via an integral over all points in space like this. And of course, that integral could be restricted to atomic basins. And the source function can be integrated over an atomic basin whereby the point of reference is moved around the basin and the source function itself is integrated over the same basin, giving an intra-atomic contribution to the electron population of that basin. And also it could be integrated over two atoms where one is the source of the density in the other. And in this case, it gives you an inter-atomic contribution, very much in parallel with the localization index and the delocalization index that I introduced earlier in the talk. And Gatti has shown that also these contributions follow a summation rule of that form with an intra-atomic contribution and a delocalization, so to speak, contribution to the population of an atom in a molecule. Given that we have this Gatti summation rule, we can also cast the integrated source function in a similar matrix format as the LDM. I call it here the source function matrix, whereby along the diagonal we put the self or the intra-atomic contribution to the population of an atom, and the off-diagonal elements, which in this case is not symmetric, like the S omega 2 omega 1 is not necessarily equal to S omega 1 omega 2, etc. But the summation rule nevertheless follows, and it would be very interesting to study and explore more this matrix, since this matrix is one that is available from an X-ray diffraction experiment through the one density. In conclusion, the LDM is an object that is very rich with information about the system that can be used to model molecular properties with high accuracy and broad range of applicability. The philosophy of the LDM can be extended to a lot of properties, such as the source function, the interacting quantum atom energy component, the IQAs, and similar properties that are expressible into a sum of self and interaction terms. The LDM modeling, as I mentioned, has an unusually wide range of applicability in predictive quantitative structure to activity relationship modeling. And finally, I would like to remind you that LDM modeling bridges the quantum theory of atoms in molecules on one side with chemical graph theory on the other, bringing these two separate subfields of theoretical chemistry together. And I'd like to thank these collaborators and students and sources of funding. And at the end, I'd like to thank you for